The next thing we're looking at in this course, and the last thing we get to look at in this course, are vectors. And so we're going to look at what a vector is. We're going to look at operations that we can perform with vectors algebraically and geometrically. So a vector is an array that has direction and magnitude. So a vector, an array with direction and magnitude. So magnitude is the length of that vector. So technically, if we have two vectors that are equivalent, they're the same length and they're going in the same direction. So if this was vector v, and a lot of times we do vectors with bold print, but when you're writing it out, it's hard to do. So you could see it with a v with an arrow over it, and that is stating that that's a vector. So let's say if v was equal to w, then basically w is going to have to, again, be the same length and direction. So it doesn't matter where I put this vector as long as it's the same length and magnitude. So if I move it over, it doesn't matter where I move it. As long as it's the same length and magnitude, they're equivalent vectors. When we're adding two vectors geometrically, what we're doing is we're taking the starting point of one vector and putting it on the tail of the other vector. So if in this case I was adding v plus w, I would take my vector v and I would start the initial point of my vector w at the end point of my vector v. And so this would be v plus w. So let's look at two different vectors and adding them. So let's look at, let's say we had v equals this vector here. And let's say maybe w I'm gonna pause for a second because that could be my doctor's office. So we're looking at adding two vectors. We have a v here. Let's look at our vector w. Maybe we have something that makes like this more. And so if we wanted to look at v plus w, we would look at our vector v. At that terminal side of v, we're going to look at putting our initial point of w. It's a little more tilted, like this. We can say that the resultant of our vector is the sum is that vector that starts from the initial side of the first vector v to the terminal side of our second vector w. This would be the resultant. Of v plus w. Not all things are commutative, which means that if we add two things, that's not necessarily the same. It is true for real numbers, and it is true for vectors. So if we had done w plus v, So if I had started out looking at my W, and then I did plus V, be the same direction, and it's parallel. And this resultant is going to be the same. So this is going to give us the same results. If we were looking at the negative of a vector, basically it's the same length, but it's a reflection across the pole. So if I was looking at, if we're still looking at this as being V, if I was to look at negative V, instead, it's going to be pointing downwards like this. So it goes in the opposite direction. And then our vector V. The zero vector has the property that if we add it to anything, we just get back that anything. If I had vector V plus my vector 0, this is equal to vector 0 plus vector V, which is just going to give me back vector V. So if we were looking at the same vectors as we had before, what about if we looked at V minus W? So in this case, I would look at vector V, which looks like this, minus vector W. So negative, I'm going to just flip. So it's kind of like V plus my negative vector W. So that switches the direction that W is going. Need to do that. How about I do this? All I'm going to do is I'm going to put that over here, and I'm going to change the direction. And so our resultant then starting at the terminal side, sorry, initial side to terminal side. So this would be our resultant. So we have an example here. We're given our vectors geometrically of V, W, and U. And in this first case, we want to find out what V minus U is. So looking at V, I'm going to try this. We have our V. Actually, and then we have our minus W. So my minus W, I'm going to go in the opposite direction. So starting here, I'm going to go this direction. I'm going to take that and I'm going to put my initial point to my terminal point. And so this vector that joins my initial point of my first vector to the terminal point of my second vector, this is going to be my resultant. So notice that the next example, we have 2 times v plus 3 times w. If we have a number out front of our vector, that is called a scalar. So we're doing scalar multiplication here. So basically that 2 in front of the vector v, that's doubling the length of v. V is going to be going in the same direction, but it's going to double. So if I look at 2 times v, I'm just going to take this and I'm going to extend it out twice to make that length. That's going to be about right here. I'm going to pull this out and move it down. So here is our 2v. And then I wanted to add 3w. So I want to take this length in here. And I want to multiply it by 3. So I want to triple that length in there. So I'm going to estimate. That's right here. So I'm going to take my 3w. I'm going to take the tail and put it on the end of my vector of 2v, put that on the initial point of 3w on that. And then our resultant is going to be the vector that joins it. So this would be our vector 2v plus 3w. So we can do this with adding more than 2 vectors. So let's look at the next example. C. C says we're going to look at 2v. Well, I already had 2v. Maybe I can. Let's just do 2v. This just helps me with keeping it the same direction. So I have my 2v minus w. So my minus w is going to go in the opposite direction. So minus w. And then plus u. So plus u here. So I'm going to take that. That's going to go right here. So our resultant, terminal side, initial side, it's going to be the following. So this was our vector 2v minus vector w plus u. So there's theorems of the properties of the magnitude of v. Magnitude of v, we can kind of write with this absolute value symbol around it, of v. we know that the magnitude, which is like the length, this has to be greater than or equal to 0. If the magnitude of v is equal to 0, then our vector v is the 0 vector. The length of negative v, the magnitude of negative v, is the same length as going in the opposite direction, positive v. If you were looking at the length of a scalar times a vector, so the magnitude of theta times v, this is the same thing as theta times the magnitude. And not theta, I put alpha. Alpha times the magnitude of v. The unit vector, let's call it u. If we look at the magnitude of u, that's equal to 1. So a lot of times we want to take a vector and we want to convert it so that it has the same direction, but it becomes a unit vector, so shrinking the length of it down to 1. So let's say that we have two vectors. So algebraically, a vector can be written AB. So it kind of looks like a greater than or less than and greater than sign on there. And those kind of give us the components of the vector, starting where our tail is at the origin 0, 0. So if I wanted to graph the vector to 1, this was going to be, I'm going to start this at this origin, and then I'm going to go over 2 and up 1. So this would be our vector 2, 1. This is if so this 2, this is the horizontal component of our vector, and the 1 is the vertical component. Another way that we can write this equivalent, this is 2i plus j, where I is the unit vector, one, 0, and where j is the unit vector that gives us the vertical component, 0, 1. So technically, all we're doing is we're looking at what is 2 times I plus j. So we're looking at 2, 0 plus 0, 1. We're adding our horizontal components. So 2 plus 0, 0 plus 1, which is 2, 1. So we can rewrite each vector in terms of the product of a unit vector and a scalar. Basically, if we're adding and subtracting vectors algebraically, we're adding our horizontal components and we're adding our vertical components. So for instance, let's say that you had V was the vector 2I plus 4J. W is the component, let's say 3I minus 2J. And we want to first find V plus W. So let's look at this. So basically, this is just saying that I'm adding 2I plus 4J plus 3I minus 2J. Let's just kind of combine like terms. So a 2I plus a 3I, this gives me a 5 times my unit vector I. And then I had a 4J minus a 2J. So this is going to give me a minus, or it's going to be a plus 2J. If I wanted to put this, I could write this also as 5, 2. Let's just look at this really quickly. Let's look at V and let's look at W, and then let's look at the resultant of adding them. So if I looked at V really quickly, so over 2, up 4, starting at the origin, this is V. If I look at W, so W is over 3, down 2. Okay, so over 3, down 2 is right here. But if I took this and let's just graph also the resultant. So 5 plus 2J. Now let's see that we get the same thing if we had done this geometrically. Let me just move this over. We have this plus this. Gives me the resultant of this. Right. Which is if my if my units were exact, that would give me the same thing right there. So we're going to get the same thing. And remember, vectors are equivalent as long as they're the same length and going in the same direction. Okay, so that's about as much time as we have to talk about vectors today, and we'll pick up and finish vectors at the beginning of next week.